Hello students, in the last section we were dealing with the stress strain curve of a metal wire. So there we discussed about elastic behavior of the wire, and after some point the wire becomes plastic behavior, the wire shows the plastic behavior, till here it shows elastic behavior. This is the elastic limit, and after that the wire shows plastic behavior, and then this is the ultimate strength, and after which the wire will break. The point E is called fracture point. That is what we studied in the previous video. By studying the stress strain curve, we can understand whether the body is ductile or brittle. What is meant by ductility? A material is ductile if we can draw that into thin wires. We can draw that into thin wires. So, after crossing the elastic limit till D, if the distance is more, that means after crossing the elastic limit, if the material can be stretched to a larger values of strain, then we can say that material is ductile. So, for ductile material, the distance between B and D is very big. That means even after crossing the elastic limit, the body can be stretched to larger values of strain. So, an object is ductile if D and E are far away from each other, or more precisely speaking, after the elastic point. I don't want to write, you just write B and D. Instead of saying D and E, you write B and E, the point B and D. Okay. So, here I will make the correction. B and E are far apart, or B and D, both of them are same. So, just you write B and E are very far apart from each other. This means the fracture point is far away from the tensile strengths. Then the material will be ductile. Now, if the fracture point is very much closer, then what will happen? If the fracture point is closer to the tensile strength, then what will happen? The object will be brittle if D and E are very close. This means the fracture point is near to the tensile strengths. So, here also you can write B and E. Example, glass, which is very brittle. If the glass jar is dropped, it will be easily break into pieces. So, is glass elastic? Glass is elastic. Okay, glass is elastic, but when it crosses the limit, when it crosses the elastic limit, it does not have plastic range of extension, so it will break easily. Therefore, I can just say like this: if I draw the graph for ductile metal, just listen. I am putting a graph for a ductile material. This is strain and this is stress. This is the straight line graph, and this point I mark that as elastic limit. And after the elastic limit, immediately it won't break. It will have a larger plastic range of extension, and then I will mark E. So, this point is actually B, and that point is the fracture point. So, distance between B and E is more. This kind of material is called ductile material. So gold, silver, copper, all those are ductile. The most ductile material is gold. Now when I draw the stress strain graph of brittle material, let us see. This is strain, this is stress, that point is called elastic limit, but you just see soon after the elastic limit it will reach the fracture point. So E is the fracture point and B was our elastic limit point. B and E are closer, so they are brittle. They are elastic, but they will break soon after crossing the elastic limit. So this is the graph for brittle material. Brittle material example, glass. So you can draw both these graphs. Now what is meant by malleability? Malleability means the material which can be drawn into thin sheets. So a material is malleable if it can be drawn into thin sheets, beaten into thin sheets. That means we have to compress them and compress them into big sheets. So it is not tensile stress we are giving compressive stress. So when I draw the stress strain graph of malleable material, it will be like this. Graph will be along this side. So here I mark compression and here I mark applied force. So when you compress also, the body will reach the elastic limit. And after reaching the elastic limit, the body will show some behavior, plastic behavior. This point is called crushing point. Crushing point. After the crushing point, the body will be perfectly malleable. So till here it is elastic. After that the elastic nature is over, but there is a region called crushing point when we compress. After that crushing point, the material will behave like malleable. How much ever we beat, it will just keep on becoming thin and thin and thin sheet. And which is the most malleable material? The most malleable material is gold. Now the next, so draw the graph of this also. This is the graph for malleable material. Now let us see what are elastomers. What are elastomers? Elastic substances like rubber and tissue of aorta have larger elastic region, but they do not obey Hooke's law. They are called elastomers. So elastomers means the materials which have larger plastic range of extension. The materials that have larger elastic range of extension. That means they can be elastically stretched to a large values of strain. When I release, they will come back. The good example is rubber. I have given two examples, rubber and elastic tissue of aorta. Aorta means the vessel in the heart. Tissue of aorta. they have larger elastic region. That means they can be elastically stretched to a large values of strain, and then when the stress is removed, they will come back to the original position. But they will never ever obey Hooke's law. Such kind of materials are called elastomers. Here you can see I have drawn a graph, that is the graph between stress and strain for the tissue of aorta. So you can see the graph is a curved line like this. It is not obeying Hooke's law anywhere. So this is the graph for aorta. Then I will show you the graph for the rubber also. So first please note down this under the heading elastomers. Note down this, then draw the graph for aorta, and now I will be giving the graph for rubber. This is the graph for rubber. So they will ask to draw the stress strain graph for rubber. This is the stress strain graph for rubber. You can see this is also a curved line. It is not coming back to the original position. Sorry, it is coming back to the original position when the stress is removed, but it is never obeying Hooke's law. So this is the graph for the rubber. Okay, so such kind of materials are called elastomers. Now, what is elastic hysteresis? Elastic hysteresis. Elastic hysteresis means it is something related to stress strain curve. Stress strain curve of a rubber or stress strain curve of any elastomer. So let us see, I am taking the case of the rubber itself, which we discussed just now. So let me draw once again the stress strain graph for rubber. When I increase the stress, strain will also increase. So rubber is not obeying Hooke's law. So the graph will be a curved line like this. This is the stretching part. Now since it is an elastomer, when I am releasing the stress, when I remove the stress, it will come back to the original position, right? It will come back to the original position, but not in the same manner. Not in the same manner, in the same pattern, not in the same pattern, which means when I draw the graph for the compression, the graph will not retrace the same path. Instead, the graph will retrace another path like this. This is for stretching, and when I release the stress, it will come back a path like this. So when I am stretching the rubber band, it will get stretched. When I remove the rubber band, it will come back, but this coming back is not exactly in the manner that it goes. Meaning the forces are different, the stresses are different, the strains are different. So the stress strain graph will not coincide in the stretching case and in the coming back case. So this property is called elastic hysteresis. So you can write like this: the fact that the stress strain curve is not retraced on reversing the strain is called elastic hysteresis. So write that statement under elastic hysteresis. So this loop that I framed here is called hysteresis loop, and area under the hysteresis loop will give the amount of energy dissipated as heat when one stress strain cycle is over. So if the material is having more hysteresis loop area, more heat will be developed by that material. So studying the hysteresis loop graph has certain advantage. For example, we want to make the tire of a car. we will select a material. We are using rubber. We will select that rubber and we will modify it in such a way that its elastic hysteresis area, this area of this loop should be less. Otherwise, what would happen if we are not doing that? Then what would happen if the area is more? When the car is going along the road, the tire will get overheated and it can burst. Okay, tire can burst. Therefore, we have to make the material having lesser hysteresis loop. Now, another example, we want to absorb more vibrations. For example, there is a huge machinery and we are keeping that machinery here. Because when the machine operates, it creates vibrations, and due to the vibrations, these tiles will break because the machine is heavy. So, what we will do is we will make vulcanized rubber and put a rubber paddle on the floor, and then we keep the machinery over there. Therefore, this rubber paddle can absorb the vibrations of the machinery, thereby preventing the breaking of the floor. So, in order to that, when we select the material, that material should have larger hysteresis loop. Only then it can absorb large amount of vibration, and that rubber material will get heated up, but nothing will happen. So, to choose different kind of materials, we have to study the elastic hysteresis loop. So, that's all about this chapter. This is a very small chapter. The chapter comes to an end with this topic. Hope you have all understood this. Thank you.